these filter coefficients may be real numbers, may be complex numbers. Alright, so either case or either cases are possible. Okay, now in the case of MVDR, well, you notice that we need to form the so-called covariant matrix. Now here the covariant matrix is formed by taking the expected value of the cross product of the snapshot. Now I have not told you yet, right, how this is actually obtained practically. We will see that later on. Okay, here, well, the signal from each tab, they are being collected and they form a vector. And this vector again is known as a snapshot vector. So here you notice that we have put this down as a row vector, but see, over here we have a transpose operation. So this is basically a column vector. Okay, so here the signal at each tab is denoted as x1. In the same column we have x1, x2. Okay, say we have 10 antennas, then this will be x1, x2, x3 up to x10. And the subsequent tab we have x11, x12, x13 up to x20. And if you have, let's say, 10 tabs, so this is one tab, second, third, and so on. So this will be the number 10 tabs. If that's the case, then you have x91, 92, and up to x100. So x, the vector x, in this case, at instant k is given by x1, x2, up to, if you have 10 antenna and 10 tabs, then the elements will be x1, x2 up to x100. So that's the meaning. Okay, and x here is a column vector. And as for the width, so you can see that each tab associated with a width number or width coefficients. So therefore, correspondingly, the width vector w, well, is given to be w1 up to w100. Alright? So let's say you have four elements, but 3 tabs. Then what would be the last element? Let's say 4 antennas, 3 tabs. So we have 4 times 3 give you 12, right? So that would be the last element. So that's something that you have to be able to understand. So what's the meaning of this structure? When they say W1, WL, and then this is WL plus 1, WL plus 2. So that's the meaning. Okay? So if you have, let's say, 4 tabs, so this will be W1, W2, W3, W4, W5, W6, and so on. Alright? Until the very last one, W12. Okay? So with that, we have the snapshot defined, we have the width vector defined. So the output is basically W times X. And while the covariant matrix is basically the same. So you can see that in terms of notation, exactly the same as that of your MVDR algorithm. And the output power is basically the same. The output YT multiplied by Y complex conjugate. And you can show that, well, in fact, easily shown that it is W transpose RW. So R here is the covariant matrix. Okay, now how about the steering vector? For the narrow band case, it is given to be this. Alright? For the broadband case, so you can see that we have actually augmented the vector with the original steering vector multiplied by ej 2 pi f for the first case, 0 times t. Second case, 1 times t. Or if you have, let's say, 4 tabs, then this will be j 2 pi f 3t. Follow? If you have 4 taps, then this will be 3t. If you have 10 taps, this will be 9t. If you have 100 taps, this will be 99t. Follow? So you can see that we have actually a very long vector. And the array response, now not only it is a direction, a function of direction, but also function of frequency, and it is given to this. So the optimization problem basically is still the same. Minimize the output power and then subject to a set of linear constraints. So the case of MVDR, the constraint equation is a single linear constraint equation, but for the broadband case, well, you have a constraint matrix C. C is given to be C1 up to Cj. So the C here is basically a matrix of this form. So let's say we have 4 antennas, all right, and the FR filter, let's say 3 taps. Then in this case, the matrix C is given to be 4 elements of 1, 1, 1, 1, and then followed by 0, 0, 0, 0, and then another group of 0, 0, 0. All right. So this is the very first column. The second column will be this, and the third column will be this. So this is the matrix C. For the case of L of 4, which means 4 antenna, and then 3 taps. So what is the dimension? So this is 3, and how about this? This is 4 times 3. Alright, so this is the matrix C. And what is the vector F there? Vector F, well, can be set in this form. So if you have 3 taps, then it will be perhaps 1. 1 corresponds to the 3 ones there, and then the rest of the elements 0. So this is one of the common setting. Okay, so again, I will not tell you how this is being derived, alright? So not our interest here, but just to tell you that it is possible to design a step processor to compute the weight using this formulation. Okay. Now the end solution, for the weight factor will be in fact similar to what you have, R inverse C, and then C transpose R inverse C, and then inverse again, and then multiply by the vector F. So comparing this, you see you have something in the denominator. You can actually bring it up, put a bracket, this term, you can put a bracket here, and then put an inverse. So what I'm trying to say here is this. The term in the denominator can be written so that you have your array weight factor given to be So you can see this is actually exactly this. And comparing the two expressions here, they are actually similar. Do you notice that? This and this, similar. And what is the F there? F is a